Hello, I'm Kenneth Cooper, and my project is the application of machine learning for the analysis of radiation-induced defects in microscope images. I'm a fourth-year undergraduate student studying nuclear engineering at Texas A&M. The sponsors for my project are the online O-REU program and Los Alamos National Laboratory. My mentors for the project are Dr. Stuart Malloy and Dr. Jonathan Gigax. I will begin by briefly explaining radiation-induced defects in materials. When a fast-moving particle from radiation collides with atoms within a material, it can damage its microstructure. As you can see in Figure 1, a particle collides with an atom causing a collisional cascade, ultimately creating a void as well as an interstitial loop. This is only an example of how primary damage of these collisions can evolve in time. If you look at Figure 2, you can see other examples such as defect migration, dislocation, interaction, and many more. This damage can ultimately cause phenomena such as swelling, radiation-induced segregation, embrittlement, and radioactivity. This can drastically change the properties of materials and is very important for any materials exposed to harsh radiation environments, such as the internal components of nuclear reactors. Next, I will briefly explain instance image segmentation using machine learning. Instance segmentation is a process of detecting and delineating each object of interest within an image. There are two parts: object detection and localization, which is a process of detecting and localizing a variable number of objects within an image, and semantic segmentation, which is a process of assigning object class to each pixel within an image. Figure 3 is a flowchart representation of an image segmentation process by a masked regional convolutional network. The input is an image. It begins with a base convolutional network along with a regional proposal network to highlight objects of interest. Next, that data is processed simultaneously with fully connected layers and a masked filter. The fully connected layers output the prediction as well as a bounding box for each proposed region of interest. The masked filter is a set of convolutional layers that perform semantic segmentation for each object of interest, creating a masked filter. Figure 4 is an example of an output image from a masked RCNN. How can a masked RCNN be used for the analysis of radiation-induced defects in microscope images? Figure 5 is a TEM microscope image of a pure iron sample that was irradiated with iron, and hundreds of voids were created. Figure 6 is that same image, but segmented using Image J. Image J is the current method of the analysis of radiation-induced defects in sample images. With this method, each defect is individually segmented by the user, which can take hours upon days to complete. For this reason, it is very prone to human and calculation errors. The goal of this project is to develop a machine learning model that can autonomously label and segment irradiation-induced defects in microscope images, as well as performing relevant calculations such as void fraction per unit depth. These are some metrics that were used in selecting the best masked RCNN library for the use of this project. Looking at these charts, it is clear that Detectron-2 outperforms all other open-source masked RCNN libraries because it has the fastest training rate as well as the highest mask average precision. Detectron-2 is developed in PyTorch and was produced by Facebook's AI research team. The models of this project were trained and tested using Detectron-2 and Google Colab documents. Before training a model, data must be pre-processed. The data for this project was annotated using VGG Image Annotator, also known as VIA. There are two separate target models. One is for dark field detection and one is for bright field detection. Figure 9 being bright field and Figure 10 being dark field. The training data for the bright field detection consisted of 79 images with over 13,000 void annotations. This data is from pure iron bombarded with iron ions at various dPAs ranging from 50 to 100 and 250 dPa. The training data for the dark field detection consisted of 41 images with over 3,500 void annotations. This data is from T91 alloy bombarded with iron ions at 250 dPa and 750 dPa. Shown in these test images are masked segmentation filters of voids using the bright field detection model. In Figure 11, in a bright field TEM image with approximately 50 voids, the model performs very well with an accuracy nearing 100%. On the other hand, in Figure 12, the model performs poorly when testing on an image with over 300 voids, as well as experiencing background texture noise. It misses nearly 50% of the voids in the test image. Shown in the test images in Figure 13 and Figure 14 are mask segmentation filters of voids using the dark field detection model. Similar performance was seen by the dark field model when segmenting larger images with a greater number of voids, but compared to the bright field model, it did not miss as many voids. Both models were fine-tuned using the baseline R50 FPN model available through Detectron 2. Test sets with images less than 100 voids were created to evaluate the performance of each model. AP is the average precision of a model and is a popular metric in measuring the accuracy of object detection models. Figure 15 and 16 are the average precisions calculated using the evaluator function in Detectron 2. In comparing the APs, the dark field detection model very much outperformed the bright field detection model. I hypothesize that there are three factors that may have caused this difference. One being that the bright field model segmented two different classes, voids and incomplete voids, but the dark field model only segmented complete voids. The next factor is that training images in the bright field model vary from 50 voids to over 300 voids in a single image, while the dark field model only had up to 150 voids in a single image. The final factor is that the images used in the bright field model experience much more background noise compared to the dark field model. Void swelling per unit depth was calculated in Python using the mask filters generated by the dark field detection model. Images from a T91 alloy sample that was bombarded with iron ions at 1000 dPa were processed through the model. The model was given the sample images cropped into sections to keep the void count below 100 in order to retain a higher accuracy. Figure 17 is the void swelling per depth that was calculated manually using image J. This took approximately 10 hours to produce. Figure 18 is the void swelling per depth that was calculated using the mask filters generated by the dark field detection model. The time it took to produce the mask filters and perform the swelling calculations took approximately 2 minutes, meaning the dark field detection model was 300 times faster and produced similar results. It could also be noted that the resolution of the graph is much greater. If further optimized, the model has potential to be more accurate and save the user orders of magnitude in time. This is a list of possible future developments in this work. The first step would be to further optimize the models by introducing more training images, manipulating the existing training sets, and experimenting with other training methods. Developing a process for manual correction, this can be done by finding a way to load images in an existing annotation software, including error bars for the void swelling calculations, creating an encoder-decoder model to pre-process noisy experimental data. This work can also be expanded beyond void recognition to include the detection of other defects such as interstitial loops and participants. In this process, more comprehensive defect statistics can be generated for TEM lamella. I would like to give a special thanks to my mentors and the O-REU program for making this project possible. Thank you for your time, and if you have any questions, please contact me at my email at the bottom.